about Gonggong. Welcome to the Gonggong episode. We're going to be looking at the dwarf planet Gonggong. As always, we're going to start by looking at Kepler's third law, which is going to help us calculate in the calculation of the semi-major axis and the orbital period, respectively, as we're going to see in the next slides. So just go through the derivation of the expressions, and then we'll apply the formulas in the next slide to come. Okay, so next we are looking at the semi-major axis. I think we are familiar with that side note there, and it's basically describing how you're going to interpret the diagram that you see with those two Gonggongs there, the two dwarf planets there. It's just the same dwarf planet but in two different positions, which we call the aphelion and the perihelion. And as you can see, it's the longest distance and the shortest distance from the sun. And we use that to calculate the semi-major axis, which is like an average distance from the sun. So we do that by saying the aphelion plus the perihelion over 2. So as you can see, the aphelion and the perihelion there, then divide by 2 and you get 67.486 astronomical units. And we should know by now that 1 astronomical unit is equal to the distance between Earth, or from Earth to the sun. So that's the astronomical unit. And we can also express 1 meter in terms of its astronomical units, which will be equal to 6.685 by 10 to the power negative 12 astronomical units. So for us to convert to meters or terameters, as we're going to do here, we just divide that 67.486. We divide it with the 6.685 by 10 to the power negative 12, which is the conversion rate for the astronomical units to meters. So as you can see, we have chosen the shortcut, or the shorter route of calculating the semi-major axis, but you can use the formula that's at the beginning of this video, where I introduced those two formulas for the orbital period and the semi-major axis. So you can use that formula for the semi-major axis with the values, but with that formula you'll be using the terameters that are here. You're not using the astronomical units. It's just a standard rule according to the international standards of calculations. We use the standard units, and meters is the standard unit. Astronomical units is just for purposes of astronomy, where we have bigger values and larger quantities to deal with. So with this shortcut, you can also use terameters. So if you're going to, you cannot mix units. So you cannot take the astronomical units for aphelion and then you take terameters for perihelion. No, you have to take the same units, the quantities with the same units, and plug them in that formula. And also with the previous formula, you're just using terameters, as I've said. So you can apply that. As you can see, I've used terameters as well in the orange part, where I've calculated with orange, and then you divide by 2 and you still get a similar answer, but now in terameters, which is similar to that of the conversion rate, as you can see, just a difference of 0.001 terameters. So that's to 3 decimal places, just for accuracy's sake. And because we've used our values in 3 decimal places in the calculation, so we're also doing the same for accuracy and to clear any uncertainties. So I think that's it for the semi-major axis. Let's move on to the orbital period. So I hope you have seen the calculation in terms of astronomical units and in terms of the terameters. You'll find the other videos. They'll be put in the description for the YouTube channel, in the description, or somewhere around this video. They'll be pinned somewhere. in the video, so that you can watch and see how you can calculate using the formula. I think it's the Mars video, if I'm not mistaken, or Venus, between the two, or Mercury. You can just check those 3 videos and see how you can use the actual formula to calculate the semi-major axis based on Kepler's third law. So for the orbital period, we're not going to use the shortcut. Let's use the equation, or rather the formula that we have derived using Kepler's third law. So, or rather from Kepler's third law. My apologies. So we'll find that the t will be equal to 2 pi square root of the semi-major axis cubed over the gm, which is the product of the gravitational constant and the mass of the sun, which is a larger mass in this case. So we plug in the values. Our semi-major axis, we have it there, 10.096 by 10 to the power 12. Then we cube that, and then we have our gravitational constant, we know the value, and the mass of the sun, we know the value, which will be in kgs. Remember, we're using standard units. So that square rooted, and then we multiply with the 2 pi, and then we get 1.749157.274 by 10 to the power of 10. And then we have to divide that by 60 seconds, 60 minutes, 24 hours, and 365 in the quarter days, or 365.25, as you can see. So we have just done that at once by multiplying, as you can see in the denominator there. So we just do it at once instead of doing step by step. We've just done the shortcut. Please make sure you understand this. Don't just follow the shortcuts in your calculations. Make sure you follow the steps, and so that you understand. You only do these shortcuts when you have a proper understanding. So you divide by 60 seconds first to get the seconds, to get the minutes. Divide by 60 minutes, you get the hours. Divide by 24 hours to get the days, and then you divide by 365 days, which are the days in a year, to get the years. As you can see at the end, we have the approximate value of 554 years, which means that Gonggong takes around 554 years to complete its orbit around the sun, to go around the sun. Okay, so now move on to the eccentricity of Gonggong's orbit. As you know, the orbit is the pathway, the imaginary pathway that the planet moves in as it goes around the star. In this case, in our solar system, the solar is a star, the sun is the star that planets orbit in the solar system. So we have that formula that we use to find the degree of eccentricity, which is the measure of the extent of degree or degree of deviation of a body's orbit from its circularity. So which means it moves from it being a circle, and then it bulges out to form an oval shape, as you can see in that side note at the top there. So that's the formula at the bottom left corner there. We have epsilon is equal to 1 minus that fraction in brackets. So it's very straightforward. It's just numbers. The A that you see in yellow there, that's the aphelion that we've looked at, and then the blue P there, that's the perihelion that we've looked at, the shortest distance from the sun. The aphelion is the abscess, which is the longest distance. Perihelion is basically periapsis, which is the shortest distance from something that, or rather the star in which the planet is orbiting, or the dwarf planet in our case. So we then plug in the values that we have, which are the aphelion and the perihelion, but here we use the terameters one. But since they cancel out, the units cancel out, you can also use astronomical units in this formula. So there are formulas where you can use both units, you can use, but you have to use the same unit when you're applying. And then there are formulas which just require standard international units. We call it the standard international in French, something like that. Maybe the pronunciation didn't come out right, but something like that. So we have that in order. So it's the aphelion over the perihelion. Then we divide that, and then we get our answer, and then we do the rest of the calculation, the board mass stuff in mathematics. You all know that. And then you get our answer is 0.4994 is our premature answer, and then our premature approximation. And then we have our final answer is 0.499. Some people say it's just 0.5, but slightly close to it being half circle, half perfect circle, and half oval. Yes, something like that. It's almost a perfect circle. It's almost an oval. It's like in the middle. So they just prefer to use 0.5, but because the scale is from 0 to 1, so 0 means it's a perfect circle, and then 1 means it is deviated from it being a perfect circle. It's now a perfect oval. Yes, let's use perfect oval. Just for your own information, the the way we can understand eccentricity is equal to 0 is we can see in the side note that eccentricity is for a perfect circle is 0. That means that the aphelion and the perihelion are the same. So in a circle, you know, we have something that we call a radius. So, or a diameter, the diameter is 2 times the radius. So it means that since a circle has a radius, it means the aphelion and the perihelion are equal, which means they are both the radii. Yes, so it's like the aphelion, the quantity of the aphelion will be a radius, the quantity of the perihelion will be a radius. They are both equal. So that will give us the 0, because aphelion divided by perihelion, it's like the same number divided into another number, it gives us 1. And then we add 1 plus 1, that 1 outside the small bracket there in the denominator, plus that 1 that would have acquired from dividing the aphelion with the perihelion, and then we get 2. And then we say the 2 in the denominator divided by the 2 in the numerator there that we can see, we get 1. And then the 1 outside the bracket minus the 1 inside the bracket that we have acquired, we then get 0. That's how we get the 0 that then tells us that orbit is a perfect circle. It's in a perfect circular shape. So I hope you can picture everything as I am saying it. Just try to understand the logic behind it. So let's move on. Okay, so now we look at orbital speed. In this case, we're dealing with the linear, not the angular. For those who are familiar with the classical physics, you know, we have what we call angular speed. Yeah, that's something that we can omit for now. But if you are very interested in looking at that, you can try and calculate it. But for now, we're just looking at linear speed for the sake of simplicity. So we have the centripetal force, which is the accelerating force of the dwarf planet, and then we have the gravitational force. Then just go through that derivation of the equation of the average speed that we're going to. We are dealing with average speed, by the way, because we have quantities that are in the average. Like the same axis is an average value, because we cannot say that that is the only value. It's not a perfect circle. The orbit is not a perfect circle, so we have to deal with an average speed, just as we have been dealing with an average distance of the planet from the sun. So that's the logic behind it, to get a more accurate value which balances out everything. I hope you understand that. So you can watch the Mars video. I will refer you to the Mars video. So watch the Mars video and get an understanding of how we derive that equation that you see at the bottom there. So now let's move on to the calculation. Okay, so we have derived the equation that we're going to use to find the average speed, which is the average speed that Gonggong moves at as it orbits the sun. But it moves at various speeds. It depends with the circumstances in space. Don't say that's the only speed it moves at. It depends, and also because of the times of the year, it has 554 years to orbit the sun. Definitely in those 554 years, there's something that's going to happen that's going to change the speed of the planet or alter the conditions for the planet to move either fast or slow. So bear with us. That's just the average, for us to be at least in the middle, for us to be at least more accurate in our understanding, so, or precise rather, in our understanding. So we have that equation derived there, and we plug in our values. We already know GM is the product of the gravitational constant and the mass of the sun, and then we divide with the same major axis that we already know, and then we get that value 3626.0670 meters per second. You can write it either way, either with the backslash or with the s to the power -1, which means the same. And then we're going to divide by 1000, so that we can have an appreciation of how fast those bodies in space move. So as you can see, we divide by 1000, we get 3.63, approximately 3.63 kilometers per second. Again, you can choose which unit you are familiar with. Then that's the 3 significant figures. So you can see 3.63 kilometers per second. That shows that it moves very, very fast compared to what we're used to on Earth. We're used to kilometers per hour, when even with our cars and planes and the like, kilometers per hour, miles per hour. But here we're looking at kilometers per second. In a second, it would have covered more than a kilometer. That's very fast. But still, it takes 554 years to go around the sun. So it tells you the scale at which we are so small compared to the bodies in space. Our degree of our size, it's so small, so small. So you can see that, yeah, we are very, very tiny, just so that we appreciate. Let's move on. So for this next segment, we're going to look at Gonggong surface gravity. And as you look at that diagram, I just want you to take note of something. That green line and the blue dot, they are inside the planet. We just couldn't find a cross section of the planet, so you can see the core and the mantle and the other parts of the interior parts of the planet. So just imagine that it goes inside that planet, that dwarf planet rather. Yes, we are dealing with a dwarf planet, don't forget that. So that line is going inside, it's not on the surface, it's not going around the dwarf planet, it's going inside. Take note of that. So we're going to use two laws to assist us in calculating the value of the surface gravity, which is Newton's law of universal gravitation and Newton's second law of motion. Very famous law, F is equal to ma. Yes. So you can read those two laws before you calculate so that you get an understanding of what I'm talking about. And then we have the equation there in blue, which is F is equal to gmm over r squared, which is based on the universal gravitation law. And then we have mg, which is based on the second law of motion, both by Newton. Isaac Newton, very popular scientist. So our g, we already know. Okay, so we cancel out the small m's first of all, because like terms, we cancel like terms when we equate. We are going to equate both equations because we are assuming that, like we did with the speed, both forces, we assume that they're equal. That's the same thing we're going to be doing here. Both forces here are equal from the two laws. So we then cancel out the m's and then we get our final answer, which is the gm over r squared. So we substitute the values, but in this case we're going to be using, we're not dealing with an orbit, don't confuse that. We're not dealing with an orbit here, we're dealing with the planet itself. So it's an object on the planet, a particle on the planet, a point mass on the planet. That's what we're dealing with. So that's why we're using the radius, the r. There is the radius squared. So we substitute our values in the new formula that we have. G is equal to gm over r squared. The capital letter G we know is the gravitational constant. The capital letter M is the mass of Gonggong. As you can see, we have the small letter m, which is the mass of that yellow dot on the surface of Gonggong. So the mass of Gonggong is 1.75 by 10 to the power 21 kilograms. Remember kilograms, the standard units. So we divide that with the radius squared, and the radius is 615,000 kilometers, or rather 615 kilometers, or 615,000 meters, and that is squared. As you can see, it's r squared, so that will be squared. And then we get our answer is 0.3088 meters per second squared. That's a premature approximation, and then the final answer is 0.31 meters per second squared to two decimal places, or two significant figures if you want to say it like that. But take note of the units. You can write anyhow, or you can put it in newtons per kg, based on Newton's second law of motion. You can rearrange that equation, F is equal to ma, so that you start with a, in our case is g, which is gravity. We're dealing with gravity, that replaces a, so it will be g is equal to f over m, which then gives that rise to the unit, which is newtons per kg, because newtons are the unit for force, and then kg is kilograms is the unit for the mass. So yeah, that's how we calculate it. And then we just want to see how that relates to the quantity of the mass of the gravity on Earth. We know the gravity on Earth is 9.81 meters per second squared, and then we say 0.31 divided by the gravity on Earth using proportion, and then we multiply by 100%, and then we get that a fraction of 100%, which is 3.2%. So it's a very, very small percentage or fraction of the gravity on Earth. So it means that it's very easy for things to float into space on Gonggong than it is to be on Earth. Okay, now we're looking at Gonggong's geometric albedo, which is basically how much Gonggong is good at reflecting light. So we're going to be looking at that extent, the extent to which it can reflect light. I'll refer you to the dwarf planet Eris video, which we know is almost a perfect reflector. Eris, it has a whitish surface, so it's almost a perfect reflector. It's very bright on the surface. So there I explained it very well, how that diagram points out to the geometric albedo and how all those values are working towards giving us the geometric albedo. And also I explained the notes that are written there So you can just go through them, and if you need clarification, I think they're pretty straightforward, but if you need clarification, go and visit the areas video. It will be pinned somewhere, just check around the video on the YouTube channel. Okay, so as you can see, we have our formula for albedo, which is A is equal to, so the A is the albedo, the geometric albedo, which is equal to, we also have what we call the bond albedo, but this is for the V band. We're using the V band magnitude. That's where we get those 3Ds. They contribute to us getting that V band magnitude, which is the H. You can watch the areas video as I said, so that you get to understand that. That'll be equal to, in the brackets, 1329 by 10 to the power negative h over 5, divided by the diameter. And that diameter, take note, it will be in kilometers. We are not following the international standards on calculation. Here we use kilometers. Yes, there's a certain reason why. Some things cancel out, but yeah, we use kilometers, as you're going to see. So the diameter in kilometers, and then the whole bracket is squared. Everything there is squared. And as you can see, we plug in the value, so h will be 2.34. That's the absolute magnitude, h for Gonggong. And then our diameter is 1230 kilometers. That's the diameter of Gonggong. And then everything we have plugged in, and then we get our answer is 0.14 as our final answer for the albedo. Meaning that, because 1 means it's a perfect reflector, it reflects all the light that comes from the sun, and then 0 means that it's pitch black, it absorbs all the light that comes from the sun. So 0 means that it absorbs all the light, 1 means it reflects all the light. So that gives us the scale on which we can see where the different planets lie. And as you can see with Gonggong, the albedo is 0.14, which means it's way close to being a perfect absorber. So it does not reflect a lot of light, which is contrary to some of the images that were taken. Some of the images would look as if it's very bright. Yes, it would look as if it's bright. Like for the Hubble telescope that you're going to see later on in this video, which was taken by the Hubble telescope by NASA and the other institutions that NASA worked with. You can see that one, it looks like it was bright, but it's actually not that bright. It's very dim, the surface. But apparently the surface used to have water, ice, and ice is very known to be the main reason why shiny surfaces reflect light. It's because ice is shiny. So in our case here, we're going to see that 0.14 means that chances are there's no ice. So that's one of the reasons why we think there's no ice left on Gonggong, on the surface of Gonggong. But we assume that it used to be there. Yes, we assume that it used to be there. There are some traces of ice that have been detected, or that are assumed to be there by scientists. But for now, we just know that with this albedo, we can see that probably there is less ice. So let's move on. Okay, now we look at Gonggong's black body temperature. So this temperature is basically the temperature that we expect to be found on Gonggong. As a cold dwarf planet, which is quite distant from the sun, we expect it to be very cold because it's far away from the sun, which is light emitting and also heat emitting. It emits a lot of energy and also UV light and all that. So because it is far away from the sun, it cannot receive much of that compared to planets that are closer to the sun, like Mercury, Venus, and the planet we are on, Earth. So we can see that with this black body temperature, that temperature does not have to have is not inspired by external elements or elements within that just develop within the atmosphere, which is different from what we have on Earth, where we have global warming, global cooling. Temperatures are just changing due to the irregularities in our atmosphere and the ozone layer and all these greenhouse gases. There's just some irregularities and some defects that are in our world, on our planet. So that's why we have fluctuating temperatures and decreasing temperatures at rates that are abnormal. But we know that there's a certain temperature that Earth will be expected to be at or that we expect Earth to be operating at, which is the same thing that we have with Gonggong here. So that's what we are trying to calculate. We're trying to calculate that exact temperature that we expect to be on Gonggong, or not exact, but an approximate temperature that we expect to be on Gonggong without any interference with other elements and defects and whatever's in the atmosphere of the planet. To get a better understanding, better technical knowledge, you can read that side note at the bottom left, and also you can check with other sources to get a better understanding of what I was trying to describe about the black body temperature. So we have that formula, which is T is equal to the fourth root of the luminosity of the sun. As we can see, that we have those quantities: the geometric albedo, star's luminosity, Stefan Boltzmann constant, and the same axis that we have at the top there. Those are the unknown quantities, or rather the quantities with symbols in the equation. Then the rest are just numerical constants. And then we have always the luminosity. We just plug in that value, and then we have our same axis. We already know it. And then we have our sigma, small letter sigma there. That's the Stefan Boltzmann constant. We just put it there. It's already stated there. And then we have finally the same axis squared, and we already know what the same axis is. And then we just square it there, and then we get our answer as 28.5046 as a pretty much approximation to 4 decimal places. And then our final answer will be approximately 28.5 kelvins to 1 decimal place. Kelvins is the standard unit for temperature. It was created after some deliberations on conventions, and found that that could be a better unit to use when you're using thermodynamic temperature. So we then might need to convert it to our degrees Celsius, which we are used to. Some use degrees Fahrenheit. You can look at the conversions for degrees Fahrenheit as well. I'm not sure about other units, but I just know degrees Celsius, degrees Fahrenheit, and kelvins. If there are other, you can use your own wherever you come from, which you use in your place. It's just so that you can familiarize with the degrees that we're using here. So we're going to use theta just to differentiate the two. So our theta will be equal to the difference between what we found there and the negative 273.16, which was found to be absolute zero. That's where absolute zero is. If you look at the pressure temperature graph, if you extrapolate it, you get to negative 273.16. That's where you get absolute zero at zero pressure. And that will give us negative 244 degrees Celsius. So it shows you that it's very cold. In the northern hemisphere, we find that most of the countries and places and continents in the northern hemisphere, they experience probably a bit more than negative 20 or negative 40, a bit more than negative 20. If it was so low as negative 40, that would be too much, but a bit lower than, a bit higher than negative 20 degrees Celsius is what's common in near the poles. But I think it can even drop further than that, but not where people actually reside. So you can see that when you're on Gonggong, it's a totally different situation. It's to the extreme of coldness. So it's with this temperature, we conclude that chances of there being life with such temperature conditions, life is quite impossible. And we are talking of life based on the organisms that we find on Earth and the conditions that we find on Earth relative to Earth. We can say that life might not exist on that planet. If it exists on that planet, then it has to have different genetic makeups, different adaptations to such conditions that we are not familiar with. But as far as we're concerned with the life that we know as life, the organic life that we know, it's very impossible to have life on Gonggong as a dwarf planet. So let's just see how we find the unit, and then we close this calculation segment. It was quite good to calculate with you. Okay, so just to be extra ambitious, let's see how we calculate the unit. So it's pretty straightforward. Maybe what you might need to know before you go on with looking at the calculation or the derivation of the unit, you need to realize that when we apply the formula, or when we substitute into the formula, in fact, when we use the formula, we do not include the quantities that do not have units, like the 16 pi. We don't include it there, and the albedo 1 minus the albedo, we also don't include it, because those two variables, they don't have they don't have units, so it's unnecessary to use them. So we just include what only has units in this type of calculation, because we're only dealing with units. So the rest will just be 1. That's the unit is 1, is of which 1 times something is just that thing, so it's unnecessary to include them. So we find that that's how we calculate. We then plug in or substitute the variables with the units, and then we derive everything, cancel like terms, and then we find our unit as kelvins. So that's basically how we find the kelvins. We actually calculate units, by the way, just so that we clear some thoughts of where do we get this unit, how do we get it. Yes, so any uncertainties have been cleared now for those who are asking where this unit kelvins is coming from in terms of how we get to calculate it. So this is how we calculate it, this is how we come up with it. We don't just guess. Science is not about guessing, it's about proving what you are guessing. So you guess, but you have to prove with empirical evidence, with empirical data, with calculations, how you are actually getting to suggest what you're suggesting. Okay, so we've come to the end of the calculation section or segment, and I think we are well versed with how to calculate these quantities now that we have more than 10 episodes from the planet series and the dwarf planet series and the podcast. The dwarf planet series is going to be changed to a podcast very soon, so just keep in touch with that probably after this video. And also, this dwarf planet is very special to Shumbafoot. It was actually discovered in the same month that Shumbafoot was created, so it plays a big role in our celebrations also, as we are celebrating Shumbafoot this month, the Shumbafoot month. And I would say happy anniversary, happy belated anniversary. Actually, it was on the 11th, but nonetheless, yeah, it's still the same month. So happy anniversary to everyone who is part of Shumbafoot. Hope you're enjoying the content that is coming to you, and more will be coming after this episode. It was quite a good episode to present to you all, and I hope you enjoyed. Hope you have understood everything. If you haven't understood, just visit other episodes and get a better understanding, and also visit other resources so that you can get a better understanding and verify the facts. It's very important in science to verify the facts so that you have a better understanding and a correct understanding with the truth. By the way, Gonggong is actually a Chinese word, so that's why you've been hearing me saying some Chinese words or phrases. And if you manage to go through the rest of the video, the calculation section, and also if you understood everything, and if you're following through calculating on your own, and also if you notice some Chinese there, I'll just say one phrase, 非常好. Well done, and hope you continue in that spirit, and enjoy the rest of the video as you get to learn more about this planet. 谢谢同学们，谢谢朋友们，谢谢大家, and enjoy the rest of the video. Cheers. More on Gonggong. Naraunda ye Gonggong.